Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. We are doing chemical properties of aldehydes and ketones, and this is our video number 5. So the reaction is Cannizzarose reaction. So aldehydes which do not contain any alpha hydrogen atoms such as HCHO or C6H5CHO benzaldehyde, they will undergo self-oxidation as well as reduction on treatment with concentrated alkali. So one will get oxidized to acid salt and the other will get reduced to alcohol. So formaldehyde will form methanol and potassium formate on reacting with concentrated potassium hydroxide. Similarly, benzaldehyde on reacting with concentrated sodium hydroxide will form benzyl alcohol plus sodium benzoate. Similarly, 2,2-dimethyl propanol does not have any alpha hydrogen atoms, so it will undergo simultaneously oxidation as well as reduction, sodium salt and an alcohol. Mechanism of Cannizzarose reaction. It is an example of hydride transfer. The step 1 is that the hydroxide ion will attack the carbon of the carbonyl group. It is a nucleophilic attack. This hydroxide ion attacks here. These electrons go up to form this alkoxide, hydroxy alkoxide ion. Now, if this hydroxy alkoxide ion is named 1, then in the second step the anion 1 will act as a hydride donor. It will give this H negative to the second molecule of aldehyde. This hydride will be given to carbon, and this is a slow reaction. Because of hydride transfer, we get C6H5 COO H and this C6H5 CH2O negative. Now, in the next step, in the final step of the reaction, the protons will be transferred, exchanged. Final step of the reaction, acid and alkoxide ion exchange proton to acquire stability. So we get a benzoate ion and benzyl alcohol. Cross Cannizzarose reaction. So Cannizzarose reaction can also take place between two different aldehydes which do not contain alpha hydrogen. For example, para-methoxy benzaldehyde and formaldehyde in the presence of concentrated alkali 50% will react. This will get reduced and this will get oxidized into para-methoxy benzyl alcohol and sodium formate or methanoate. Then if the Cannizzarose reaction occurs within the same molecule, that is one carbonyl group gets reduced and the other one gets oxidized, then it is called intramolecular Cannizzarose reaction. For example, glyoxal when heated in presence of alkali will form, this will be reduced into hydroxy group and this will be oxidized into carboxylate anion. And then this molecule, sodium glycolate, when treated with dilute HCl, Na will be replaced with H to form glycolic acid. This is intramolecular Cannizzarose reaction. Next reaction is reaction with aluminium ethoxide. It is called Tishenko reaction. This is a modified form of Cannizzarose reaction. All aldehydes, whether they have alpha hydrogen or they do not have alpha hydrogen, can be made to undergo Cannizzarose reaction, that is self-oxidation as well as reduction on treatment with aluminium ethoxide. However, under these conditions, the alcohol and acid form will react together to form ester. For example, when acetaldehyde is heated with aluminium ethoxide, ethanol and the other ethanoic acid will be formed. These two will combine, water will be eliminated, OH and H, and ester will be formed. Similarly, when propanol reacts, propanoic acid and propanol are formed. They react with each other to form propyl propanoate ester. Similarly, acrolein, when heated in presence of aluminium ethoxide, again will combine with each other to remove water after self-oxidation and reduction to form an ester, which is allyl acrylate. So this reaction is called Tishenko reaction. Halogenation. Aldehydes and ketones having alpha hydrogen undergo halogenation under suitable conditions in which the hydrogens are exchanged or replaced by halogens. So all three alpha hydrogens will be replaced with Cl3. We get chloral along with HCl. Similarly, acetone can also undergo halogenation, chlorination to form a mixture of chloropropanones. Next reaction is action with Schiff's reagent. Now, Schiff's reagent is a pink-colored aqueous solution of rosanilin hydrochloride, which has been decolorized by passing sulfur dioxide. So, when aldehyde is made to react with this colorless or decolorized solution of Schiff's reagent, it restores, the pink color is restored. So, we can identify the presence of aldehyde by this test. So this reaction is known as Schiff's test and is used as a test for detection of aldehydes. Ketones do not give this test. Polymerization reactions. Aldehydes and ketones can undergo polymerization reactions under different conditions. For example, first is polymerization of methanol or formaldehyde. So when formaldehyde is allowed to stand at room temperature, it will slowly undergo polymerization and form a white colored solid called trioxane or metaformaldehyde. 3 molecules of formaldehyde join together to form a cyclic product. So the electrons of double bond will move here to form a bond here. Similarly, here and here a bond is formed. So this metaformaldehyde is formed. 3 molecules of formaldehyde have joined to form a cyclic product, trioxane. Evaporated to, if aqueous solution 40% of formaldehyde is evaporated to dryness on a water bath, it will form a white solid called paraformaldehyde, where a linear polymer is formed. CH2O will combine with itself n times to form this paraformaldehyde. The value of n can be between 6 to 50 and the product is known as paraformaldehyde. On heating, it will regenerate the formaldehyde. Then formaldehyde can condense with phenol in the presence of a base such as NaOH and form cross-linked polymers called Bakelite, also known as synthetic polymers. So these are also, Bakelite is also called phenol formaldehyde resin. It is a condensation polymer and is obtained from phenol and formaldehyde in the presence of either an acid or a base. So when phenol reacts with formaldehyde, the H at ortho position of phenol, ortho or para position of phenol gets added up to the double carbonyl bond. So H goes to oxygen and CH2 gets attached. So we get orthohydroxybenzyl alcohol and parahydroxybenzyl alcohols. These will further react with phenol to form compounds having methylene bridges either at ortho or para or both at ortho and para position with respect to phenolic group. So if only ortho molecules polymerize, they form a linear polymer known as Novolec, where CH2 is acting as a bridge between 2 phenol groups. And this occurs an n number of times and the polymer Novolec is formed, which is used in paints. And if Novolec is further heated with formaldehyde, it will undergo cross linkages as well along with linear linkages to form a cross-linked polymer Bakelite. Alternatively, we can combine or polymerize orthohydroxybenzyl alcohol and parahydroxybenzyl alcohols to form this cross-linked polymer where CH2 is acting as bridging, joining the phenol linearly as well as cross-linked. This Bakelite, its uses When it is with low degree of polymerization, it's a soft bakelite and is used as a glue for binding laminated wooden planks and in varnishes. And when with high degree of polymerization, it forms hard bakelite, which is used in the manufacture of combs, fountain pens, barrels, phonograph records, electrical switches, and handles of various utensils, formica tabletops, and many other products. Polymerization of acetaldehyde. When acetaldehyde is treated with a few drops of concentrated sulfuric acid at room temperature, 298 Kelvin, a rapid exothermic reaction occurs in which again there is 3 molecules of acetaldehyde will combine to form a cyclic compound paraldehyde. It is a cyclic trimer. Paraldehyde is a sweet-smelling liquid and is used as in medicine as hypnotic. Its boiling point is 401 Kelvin. On the other hand, on cooling from acetaldehyde with a few drops of concentrated sulfuric acid at 0 degrees centigrade or dry hydrogen chloride gas at 0 degrees centigrade, 4 molecules of acetaldehyde will combine to form a cyclic product which is known as meta-aldehyde. It's a 8-membered ring. It is this meta-aldehyde is a white solid, boiling point 519 Kelvin. It regenerates acetaldehyde when distilled with dilute sulfuric acid. Next is polymerization of acetone. When treated with dry HCl gas, it will give macetal oxide when 2 molecules of acetone join together, and 4-on when 3 molecules of acetone join together. So when 2 molecules join, the oxygen of one and 2 alpha hydrogens of other combine to form water, and they join by double bond forming macetal oxide. 4-methyl, 1, 2, 3, 4-methyl pent 3 in 2-on. And if 3 molecules combine, then the oxygen of one acetone will combine with 2 alpha hydrogens of other. Similarly, the oxygen of the third one will combine with 2 alpha hydrogens of this one, middle one, and the 3 combine together to form this product, which is commonly known as 4-on, and IUPAC name is 2,6-dimethyl hepta-2,5-diene-4-on. When treated with sulfuric acid, 3 molecules of acetone will combine to form this cyclic product, mesitylate. Substitution reactions of benzene nucleus in aldehydes and ketones. Now, aldehydic and ketonic groups are meta-directing groups. They direct the electrophile to meta position. So, substitution will occur at meta position. Halogenation, when reacted with chlorine in presence of ferric salt, ferric chloride, chlorine gets attached at meta position and HCl is formed. So, metachlorobenzaldehyde. Similarly, acetophenone will combine with chlorine in the presence of ferric chloride to form metachloroacetophenone and HCl. And when treated with nitrating mixture of concentrated nitric acid and sulfuric acid, nitro groups gets attached at meta position. Metanitrobenzaldehyde will be formed with benzaldehyde, and metanitroacetophenone will be formed with acetophenone. Similarly, on reacting with concentrated sulfuric acid, benzaldehyde will form meta-sulfonic acid derivative, meta-carbaldehyde, benzene sulfonic acid, and metacarbaldehyde acetophenone. These products will be formed. That's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.